Hello and welcome back to Anton Math. Now in this video we're going to be doing some worked examples using the binomial theorem. And first we're going to do a counting problem, and after that we'll do some expansion problems for practice on that. Now how many ways are there to choose 3 or more marbles from a bag of 11 marbles? Now using just what we know about counting, I know that there's going to be 11 choose 3 ways to choose 3 marbles. Now there's going to be 11 choose 4 ways to choose 4 marbles, 11 choose 5 ways to choose 5 marbles, and so on all the way up to 11 choose 11 ways to choose 11 marbles. So this is a lot of computation, and we want to explore how the binomial theorem is going to make this easier. Well, I can write this sum as the sum where k goes from 3 to 11 of 11 choose k. Now I know that I can also write this as the sum where k equals 0 to 11 of 11 choose k. Now I've added 11 choose 0, 11 choose 1, and 11 choose 2 to this side, so I need to subtract as well 11 choose 0. I need to subtract 11 choose 1, and I need to subtract 11 choose 2. Now from our result from the last video, I know that this sum here, this is the sum of all the coefficients for all the k's 0 to 11 of 11 choose k. So that sum right there is just going to be 2 to the 11 from our result from the last video. 11 choose 0 is just 1, 11 choose 1 is 11, and 11 choose 2 is 55. So we've cut down our computation a bit, right? 2 to the 11 is 2048. And I'm subtracting all of these over here, so I'm just going to be subtracting 67. And this is going to give me a total of 1981. So there's 1981 ways for me to choose 3 or more marbles. Now there's nothing wrong with just if we had just straight computed this out from the beginning, but we see how much easier it is to use the tools of the binomial theorem to be able to compute this instead of adding all these, figuring out what each of these coefficients are individually and then adding all of them together, right? It's quite tedious. Okay, so that's an example of how we can use the binomial theorem in a counting application. Anytime we're looking at a range that it can be, we can segment that off and use our binomial theorem to kind of make it an easier computation. So now let's look at some expansion problems. And when I say expansion problems, I mean just using the binomial theorem to do an expansion. So for example, let's look at x plus 1 to the 6th. Let's say I want to expand this out. So instead of a product of x plus 1s, it's just a single polynomial. Well, using my binomial theorem, this is going to be 6 choose 0 times x to the 6th, 1 to the 0, but I'm just going to omit the 1s, plus 6 choose 1, x to the 6 minus 1, which is 5, 1 to the 1, which is just 1, plus 6 choose 2, x to the 6 minus 2, or x to the 4, plus 6 choose 3, x to the 6 minus 3, or x cubed, plus 6 choose 4, x to the 6 minus 4, or x squared, plus 6 choose 5, x to the 6 minus 5, or x to the 1, plus 6 choose 6, x to the 0, 1 to the 6, so just plus 6 choose 6. Now this is where Pascal's triangle that we talked about before can come in handy. Let's say I don't want to sit down and compute out all 7 of these coefficients that I need to finish out this problem. Well, I can just calculate out the first couple of rows of Pascal's triangle. Looks something like this, right? And I notice here, this is my row for n equals 6 right here. I know that because 6 choose 1 is 6, so my second term should be 6, and that happens on this row. So my coefficients are going to be 1, 6, 15, 20, 15, 6, 1 in order. It's very important, in order. So finishing out our problem over here, this is just going to be, with reference to that table, x to the 6th plus 6x to the 5th plus 15x to the 4th plus 20x cubed plus 15x squared plus 6x plus 1. All right? So not bad. It's a much easier process than if we actually took this here and did repeated multiplication and just tried to compute it out. We can use the binomial theorem and get a result almost immediately. All right? Now let's do one that's a little bit more tricky. It's not always going to be x's and 1's. So you'll often see something like, let's say I have x minus 2y cubed. Now here, this entire minus 2y, this is going to be my y term in my binomial expansion. All right? It's very important that we do this entire 2y, and we can think of it as this is x plus negative 2y cubed, right? This negative is a part of this term. So when I look at the binomial expansion, this entire negative 2y is going to take the place of that y that we had in our definition. So when I do this out, this is going to be 3, choose 0, x to the 3 minus 2y to the 0, plus 3, choose 1, x to the 3 minus 1, which is 2, minus 2y to the 1, right? Remember, this power is just k, this power is n minus k, plus 3, choose 2, x to the 1 minus 2y squared, plus 3, choose 3, x to the 0, which is just 1, minus 2y cubed. Now looking at my Pascal triangle again to get these coefficients, looking at the row with 3's, it's just 1, 3, 3, 1. So that's what I'm looking at here. So 3 choose 0 is 1, negative 2y to the 0 is 1, so I'm going to have 1x cubed, plus, now 3 choose 1 is 3, I have 3x squared times a negative 2y. 3 choose 2 is 3, so I have 3x times a negative 2y squared. The negative 2y squared is just 4y squared, right? The negative 2's cancel with each other. Plus, now 3 choose 3 is 1, so I just have negative 2y cubed, but that's the same as negative 8y cubed. So finishing this out, this is going to be x cubed minus 6x squared y plus 12xy squared minus 8y cubed. Okay. Now the most common mistake on these types of problems is students either forget to include the negative in each of these terms, or they forget to take the power to the 2 as well. So for example, here you might have something like minus 2y cubed for this last term. That would be a common mistake, where you're just kind of holding the minus 2 as a constant and only raising y to the power. Very common confusion. It's important to note that here y is not acting in y. Let me go ahead and rewrite our binomial equation here, binomial theorem. X plus y to the n equals k from 0 to n of n choose k, x to the n minus k, y to the k. So it gets a little bit confusing when we have these problems with y's in it, because we think, well, by my theorem, I'm just going to have this y to the k. And this is a constant, so it'll just be here, and I'll multiply by negative 2. That's where we get this kind of mistake from, right? So it's very important to note that here, I don't have y, I have minus 2y. And that plays the same role as this entire y does. So we saw when we did the problem, we were raising minus 2y to the power of k, not just raising y to the power of k and then multiplying by minus 2. Okay, so these are pretty easy to make up. I do encourage you to practice a couple of these on your own. You can check your results on Wolfram Alpha, things like that. But this is a very important skill to have in general in mathematics, and particularly when we're talking about either polynomial expansion or anything to do with counting or combinatorics, as we call it. All right, that's the end of this section on the binomial theorem, and we'll see you next time.